triangle, you guys have the formula given to you. Let me grab a pen real quick. I'm going to give you a formula chart for your midterm coming up, and it will have the area of a triangle formula on it. Base times height divided by 2, or some people prefer this formula 1/2 base times height, but it's the same thing. What you want to make sure of is that when you're using the base and the height of your triangle, that you identify the base and the height as always the two perpendicular pieces. So like the height is 7, and the perpendicular piece is going to be down here at the bottom. If there was a number up here, like let's say this is 14, then you would not choose that one because he's not perpendicular to the height. So base and height are always perpendicular. Now the question is whether or not I choose the 13 for the area of the triangle or the 18. But if I'm trying to find the area of this shaded triangle, then I just want to use the 13. So base, 13 times height, 7, all over 2. And that should be pretty basic for you guys, just a review of what you've done in the past. So 13 times 7 divided by 2 comes out to 45.5. Same thing for this one. Notice it gives you the base is 6, the height is 4, and all over 2. So 6 times 4 divided by 2, which comes out to 24 over 2, which is 12. Same thing for these guys. I'm going to kind of go a little bit faster here because I think this is review for you. This problem right here is a little bit different though, because it gives you the area and it gives you the base, but it doesn't give you the height. So whenever it gives you the area, you want to work backwards. Do you see how A is over here on the left? Well, that's what I'm going to plug in for the area, 10.92 equals. I know the base is 2.8. I'm looking for the height, so that'll be my variable, all over 2. So I just want to work an example of working backwards for you. Base is 2.8, x, all over 2. And there's two ways to work this. The first thing you can do is simplify this fraction right here, 2.8 divided by 2. Or you can cancel out the fraction by multiplying by 2. A lot of students like to do this first. But either way, you should get the right answer. So 2 times 10.92 comes out to 21.84 equals 2.8x. Then 2.8x and equals 21.84, so you need to divide by 2.8 on both sides. So cancel out here, and you're left with x equals 21.84 divided by 2.8 leaves me with a height of 7.8. So that's an example of working backwards. You want to plug in what you know. The area was the 10.92 equals base times height over 2. And the next type of area problem you might see is something like this. The legs of a right triangle are 5 and 10. What is the area? Well, what we know about a right triangle is it has 2 legs and 1 hypotenuse. So the hypotenuse is always going to be across from the right angle. I say you can kind of use that right angle like an arrow. It points at your hypotenuse. But the other 2 guys, those are just called legs. And so 1 leg is 5 and 1 leg is 10. And the reason we can find the area of this triangle is because the legs are perpendicular. So that's our base and our height. Remember, whenever you're trying to find the area of a triangle, you always want to use the perpendicular sides. So area is base times height divided by 2. So that'd be 5 times 10 over 2, which comes out to 25. Okay. You can use the chat feature down at the bottom left if you have questions. You can stop me. Okay, but we're just doing a little bit of review. I even think Pythagorean theorem should be reviewed for you guys. This formula will also be given to you on your formula chart for your midterm. The biggest part to remember about your your Pythagorean theorem is that the c squared is always your hypotenuse. Okay, so c squared is always your hypotenuse. A and B can be either leg, it doesn't matter, but the c squared is the hypotenuse. So let's look at number 1. Okay, which section of the triangle is the hypotenuse for number 1? What number or letter? What do you guys think? You can use the chat feature, you can use your pen. Which side is the hypotenuse? Any ideas? Okay, it's 34, perfect. Your 34 is your hypotenuse because it's across from the right angle. So when you're setting up the Pythagorean theorem, you would say x squared plus 16 squared equals 34 squared. And you would solve. X squared just stays x squared. 16 squared comes out to 256. 34 squared comes out to 1156. To get x by himself, we're going to subtract 256 from both sides. Minus 256 comes out to 900 equals x squared. Now to get x by himself, notice he's being squared, so the opposite of something squared is the square root. The square root. And the square root is always the last thing that you want to do when you're solving for your Pythagorean theorem. So x equals the square root of 900, which is a perfect square. It should be 30. Perfect. So x equals 30. Notice the hypotenuse is always the longest side. So when you're finished with your answer, you want to make sure that you didn't get one that's bigger than that hypotenuse, because then you'd be wrong. Let's try another one. For number 2, x is going to be the hypotenuse because it's across from your 90-degree angle. So you would set up your equation, 6 squared plus 9 squared equals x squared. 6 squared is 36. 9 squared is 81 equals x squared. 36 plus 81 comes out to 117 equals x squared. Notice our directions here say write your answer in simplest radical form. Simplest radical form is where you take the square root of both sides and it'll cancel this guy out. You take the square root of this side. And you want to simplify that radical. It's not asking for a decimal here, it's asking for a simplified radical. So you want to think about the factors that can break up into, that 117 can break up into. And in this case, I don't think there's anything that can break out of 117. So our simplified radical will just be x equals the square root of 117. Okay? All right. I want to skip those 2 problems just to save some time. I want to go down here to this problem. Is a triangle with the legs of 5, 10 and the hypotenuse of 12 a right triangle? If ever you're trying to figure out if a triangle is a right triangle, you just want to plug it into the Pythagorean theorem, 5 squared plus 10 squared, and see if it equals 12 squared. So 5 squared is 25, 10 squared is 100, equals 144. 25 plus 100 is 125. Does that equal 144? No, it does not. So this is not a right triangle. Okay. All right, so I see that somebody mentioned that 117 can be divided by 3. You are correct in that 117 can be divided by 3, so we could break this guy up into 3 and 39. And then we can break the 39 up into 3 and 13. Good catch there. Okay, so what that means is that we can simplify this radical of 117 by breaking these 2 guys out of the radical to get 3 radical 13. That'll do it. All right. Next, you'll see problems like this, asking you to find the missing sides of the triangle. Specifically, it'll ask for this side right here, YZ. Okay. And in this case, whenever you have two sides of a right triangle and you're missing one of them, you just want to use Pythagorean theorem again. So you could use these two sides and this one to use Pythagorean theorem, or you can kind of ignore this triangle altogether and use these two sides with Pythagorean theorem to get that one. So I'm just going to ignore this triangle. I know this is a right triangle, so I'm going to set up my Pythagorean theorem. 30 squared plus x squared equals 34 squared. And solve from there. 30 squared we know is 900 plus x squared equals 34 squared. Comes out to 1156 like we did before. Subtract 900 from both sides. Minus 900. Comes out to x squared equals 256. Square root. So square root of 256 was 16. Okay. So that's one way to solve for that missing right triangle. All right. So you guys, on the last unit, you were talking about triangles that were congruent, and y'all looked at side, 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 angle, side, angle, side, angle, and angle, angle, side. And we talked about in our last Blackboard about HL as well, but they also added LL, LA, and HA as their congruence postulates. And these three are specific, well actually all four of these are specific for only right triangles. Only right triangles can be proven by these. Okay. And when you're looking at these types of congruent postulates, we don't need to consider the right angle because it's assumed that it's right. But you can look at the right angle when you're looking at these postulates. So for instance, if we were trying to prove these two triangles congruent, the first thing I would do is mark what they share. And then I know that I've got one angle and two sides. And I would say that's angle, side, side. But I know that angle, side, side is not one of my congruence postulates. But it's a right triangle. So I've got hypotenuse congruent to hypotenuse, which is this guy. And one of the legs congruent to another leg. So this guy would be an example of HL. Same thing for the next one. They share the side right here. Angle, side, side is not one of our postulates from before, but I do know that the hypotenuse is congruent to the hypotenuse, and one of the legs is congruent to another leg. So this is an example of HL. Then you've got this triangle here, or sets of triangles, and we know that the vertical angles are going to be the same. So if we read from top to bottom, it'd be angle, side, angle. But this is also an example of LA, because I've got a leg and an angle congruent to a leg and an angle. It's not going to be HA because the hypotenuse is not congruent to the hypotenuse. And it's not going to be leg, leg because both legs aren't congruent to both legs. On this next example, you've got side, angle, side, going from top to bottom and left to right. Side, angle, side is one of them. But it could also be proven by leg, leg, because both of the legs are congruent to both of the legs. It's not going to be HA because the hypotenuse is not congruent to the hypotenuse. It's not going to be LA because there's no other angle congruent to any other angle. Then you've got this true or false statement. It says based only on the given information, is it guaranteed that these two segments are perpendicular? Well, based on AD is congruent to BD, and I know that this side is congruent to itself. Is there going to be enough information to say that those two lines are perpendicular? Well, in this case, there's not, because I can't prove these two triangles exactly the same. If I could prove those two triangles congruent, then it would be enough to say this was a perpendicular bisector. But because side is not one of our congruent postulates, and I don't know this is a right triangle, I can't use any of those, so this is not enough information. Okay? Please feel free to stop me, you guys, with the chat feature if you have any questions. All right? I also made a video on these. If you get to this lesson and you're stuck, go ahead and check out Moodle, because there's a video of those being worked out as well. Angle bisectors, remember bisect means to split into two equal parts. So I'm bisecting an angle. Makes congruent right triangles. So if you're given that this angle is 28, then I know this angle is 28 because it's an angle bisector. Angle SPQ would be the addition of 28 plus 28. And if I knew that these two were angle bisectors, then I would also know that this piece right here is congruent to this piece right here. So whatever those two are the same. Same thing down here. If this is an angle bisector, then this is 35 degrees. This is 11, this is 11, and whatever this guy is going to be the same thing. Angle bisectors. This is probably one of the trickier parts of your Unit 4 lesson. There's 3 triangles here. So hopefully you guys see 3 triangles. A small one, a medium one, right here, and then a large one, all the way around. And what this is a memory tool on how to set up proportions using similar right triangles. Okay, so just looking to set up a proportion. Now, notice our sides are outside the triangle. And my goal here is to just set up a proportion with corresponding sides. But because all my triangles are turned funny, it's kind of hard to see. So that's why we come up with a memory tool called the boomerang. The boomerang is going to help us set up our proportion, because wherever the boomerang goes, you're going to write down your proportion based on where the boomerang travels. So the boomerang goes across, back this way, turns around, and then comes back here. And it always stops at the altitude. The altitude is the height of the triangle. So the altitude right here is perpendicular to this base. It always stops there. So I had some animation in here, but I don't think it came through on my Blackboard. But the boomerang would travel across the hypotenuse here, so that'd give us 16 over x equals x over 9. So that's how we get this proportion right here to set up. And then to solve proportions, we always cross multiply. X times x is x squared. 16 times 9 comes out to 144. And then, like we were doing before, to solve for x, you want to cancel out that square with the square root to get x equals 12. So similar right triangles has 2 memory tools. One is called the boomerang, and the other one you'll see here in a second. Okay, this is another example of the boomerang, where now I'm going to throw it from down here because I'm looking for this side y. So notice, if I was to throw the boomerang from the top, it would go across this way, back here, and then stop at the 9. But that doesn't help me solve for y. So I don't want to do that. I want to throw it from the opposite side of y and set up the proportions based on where the boomerang travels. So it'll travel up 16, down to the y, back up, y, and then I'll stop at 7. So 16 over y equals y over 7. Cross multiply, and you get y squared equals 16 times 7, comes out to 112. 112 can be broken down into 16 and 7, of course. 16 can be simplified into 4 and 4. Just like when we were simplifying our radicals before, you pull out a group of 2 on the outside of the radical, and then the 7 is stuck in. So that's how we get x is 4 radical 7. The other memory tool is called over, up, down, over. And the reason we use this one is because now our side is on the inside of the triangle. This is Sally. Hi, Sally. She's going to run and then jump and then come back down and keep running. And that's how we set up our proportion for when there's a side on the inside of our triangle. 9 over y equals y over 4. And you could also start Sally on the other side and it wouldn't matter. You would still get the same answer. So you cross multiply and solve to get y equals 6. If this is making no sense whatsoever, hopefully what you'll see is as you work through the lesson, you'll see the types of pictures that we're talking about are always going to be a right triangle with an altitude drawn, and you're going to have a missing side either on the outside with these 2 given, or you're going to have a missing side on the inside, and you'll have to do over, up, down, over. But that's the type of problem you want to look for to use our memory tools. And I also made another video on my Moodle website of just these types of problems, okay, to help you find those corresponding sides. Here's another example of over, up, down, over. 6 over 4 equals 4 over y. You would cross multiply. Here's another example of what you might see on the quiz. For instance, here, notice all my sides are outside the triangle, so that's going to be boomerang. And I'm going to throw the boomerang from B because I don't care about this side right here. And if I threw it from C, then it would go over here and it'd catch AB, and I don't care about AB. So if I was going to solve for x here, I would do 20 over 15 equals 15 over x. 20 over 15 equals 15 over x. And then we would solve by cross multiplying. 20x equals 225, divide by 20, divide by 20. Comes out to 11.25. This example here, we would do over, up, down, over. But notice, I don't know this missing side right here, but I do know the whole thing is 25, and this piece right here is 16. So I'm going to take 25 minus 16 to get 9, and that 9 goes right here. So now when I run Sally, over, up, down, over, just going to use the 16 over the h equals h over the 9. Okay. Keep on moving. Setting up proportions for similar right triangles. If the triangles are side by side, then you just want to match those corresponding sides to help you find your missing sides. So notice CD is going to be corresponding to BC. So X is going to be corresponding to the 20 minus X. Oops, that's an X. And we can set that equal to our corresponding sides over here. Now notice, X is a small triangle, so the small triangle on the bottom is what I'll need to put over here, 7 over 21. When you do this, when you cross multiply, you want to make sure you put parentheses around here so that you distribute that 7 in. So you get 7 parentheses, 20 minus X equals 21X. Don't forget to distribute. 140x, or 140 minus 7x equals 21x. Add 7x on both sides. 140 equals 28x. And then divide by 28. We get 5. Okay. Oops. Divided by 28. X equals 5. Okay. Alrighty. Moving on. Based on the information given, is it guaranteed that these two triangles are similar? Well, similar triangles can be proven by our sides being proportional, by two sides proportional and one angle the same, or just two angles the same. And in this case, we're just given some angles, so we want to look to see, are the two angles the same? Well, I've got 90 equal to 90, but that 52 doesn't equal that 38. But I do know that I can solve for those missing angles in the triangle just by adding and subtracting from 180. Okay, so 90 plus 38 comes out to 128 plus x equals 180. Subtract from 180 on both sides to get 52 degrees. So this guy is 52 degrees. Now I've got two angles exactly the same. So yes, these are similar by angle. No questions so far? All right. If you've been zoning out, which I know is easy to do, you need to focus back in, because we are about to get into special right triangles, which you will see on the SAT and ACT, and you will see them kind of coming back throughout the course. So you just want to be really familiar with these special right triangles. And what makes them special? Well, special right triangles have a pattern to them, and they all go by the same pattern. So we're going to start with our 30, 60, 90 special right. Notice the 30 is an angle measure. The 60 is an angle measure in the 90. If you have just one of the angles is 30 and the other one is 90, you know automatically that the last one is 60. So it'll be a 30, 60, 90, just like here. This guy is going to be 60. This one's going to be 60 because they add to 180. All 30, 60, 90s follow the same pattern. And this is going to be the formula that you'll see on your formula chart. It'll have a 30, a 60, and a 90. Across from the 30 is going to be an x. Across from the 90 is a 2x. And across from the 60 is an x radical 3. That'll be the pattern that you're given on the SAT formula chart and on my formula chart for your midterm. Okay? And so the steps are, first, I want you guys to make sure you label the pattern. Okay? Second, I want you guys to solve for x. And then third, we're going to plug x in. Okay. This is probably one of the more difficult concepts that we teach in geometry, so you definitely want to pay attention. Y'all ready? Across from the 30, he's the x side. Across from the 60, he's the x radical 3. And across from the 90, he's the 2x. So I labeled my pattern. Next, I need to solve for x. Notice x equals 2, because the x that I labeled is equal to the side that was given to me. So this one's actually a really easy example, because I already know x equals 2. Well, then I can plug in x. If x equals 2, then 2 times 2 is 4. And if x equals 2 here, then I can plug in 2 here and get 2 radical 3. Does that make sense? Let's try another one. Okay. First step, label my pattern. Across from the 30, he's the x side. Across from the 60, he's the x radical 3. And across from the 90, he's the 2x. Now I need to solve for x. So I set this side I'm given, that 6, equal to the pattern. And I solve for x. So to get x by himself here, we're just going to divide by 2 to get x equals 3. I solve for x. Now I plug x in. Well, if x equals 3, then this side right here is 3. And this side right here is 3 radical 3. Okay? Let's try this one over here. I'm going to say that the side that we're missing here, let's say he is 6 radical 3. Okay? So I'm going to start just by labeling my sides. Across from the 30, he's the x side. Across from the 90, he's the 2x. And across from the 60, which would be right here, is going to be the x radical 3. Well, if 6 radical 3 equals x radical 3, then the x is the 6. So you can do this mathematically by dividing by radical 3 on both sides. Cancels. But you'll just be left with x equals 6. So if x equals 6, then you come back over here, you plug x in. 2 times 6 is 12. And it's just that simple. The hardest part is when you're given the x radical 3 equals a whole number. Okay, and that's where what I would do is go ahead and plug it into your calculator, get a decimal, unless they make you get a radical. Okay, if they make you get a radical, then what you would do is solve for x, just like you were normally going to do, divide by radical 3. Divide by radical 3. So you get x equals 5 over radical 3. And what we know from algebra is we can't leave a fraction like that. You have to rationalize the denominator. So this is kind of a tricky part, where you're going to have to multiply by radical 3 over himself to get x equals 5 radical 3 over 3. So that would be the x, which we know is across from our 30, which would be this side right here. The 2x is our hypotenuse, 2x. So it would be 2 times this, which would come out to 10 radical 3 over 3. Okay? That's the trickiest kind. Otherwise, they're pretty simple. When you're given the side that's across from the 30, he's the x side. Across from the 90, he's the 2x, and across from the 60 is the x radical 3. You solve for x and you plug it in. 2 times 12 is 24. And then you plug 12 right in there to get 12 radical 3. Okay? All right. Let's take a look at the other type of special right triangle. The last type of special right triangle is going to be a 45, 45, 90. And your pattern is just going to be a little bit different. I think it's a little bit easier. Your pattern is x, x, x radical 2. The reason these are both x is because if it's a 45, 45, 90, then that automatically makes it an isosceles triangle. So x, x, x radical 2. But just like on the other page, we're first going to label our picture. Then we're going to solve for x. And then we're going to plug in. So I'm going to label my picture. This side is x. This side is x. And this one equals x radical 2. I'm going to solve for x just by getting x by himself. We divide by radical 2. Divide by radical 2. So the x equals the 3. So this side will be 3, and this side will be 3. Same thing on this one. Label your sides, x. This one is the x, and this one is the x radical 2. So if x equals 4, Then I can plug in here for 4 and here for 4 radical 2. Okay. Try a tricky one here. Label our sides. This one's x, this one's x, and this one equals x radical 2. Solve for x. So to get x by himself, we divide by radical 2 on both sides. So that x equals 15 over radical 2. Notice it cancels on the right because it's radical 2 over radical 2, but it doesn't cancel on the left because there is no radical 2 on the top. That's when the radical gets stuck on the bottom of your denominator, and we can't leave it like that. We have to rationalize our denominator. So you multiply by radical 2 over himself to get 15 radical 2 over 2. That guy is your x. X equals 15 radical 2 over 2. So that would go here and here. Okay? All right. Know that you can always come back and review this Blackboard recorded session for these 2 slides. If you're going through that lesson and you have no idea what's going on, then pull this Blackboard recorded session back up and see if you can't read through Apex and then come back here and relearn, get retaught, that sort of thing. Okay, use this recording to help answer your questions. So we're going to move on to trig, and trig is just a short name for trigonometry. And what you want to do is go ahead and get a calculator. So like I said earlier, you can go to Google, and if you go to Google and type in calculator, it'll bring up this guy in the very beginning, the very top of the page. Okay, so this is one type of calculator you can use. Know that on your midterm, I'll provide a calculator if you don't have one. If you want to use your own, I'm fine with that, but if you don't have one, I'll provide you with one. And if you're using the Google calculator, please make sure it's on degree mode. So this guy right here is like a toggle switch. You want to make sure it's on degree mode for all trig functions. Same thing if you're using a TI-83, TI-84, you just want to hit the mode button on your calculator and make sure that the word degree is highlighted. Okay? So automatically, most calculators are not in degree mode, so you just want to make sure they're in degree mode. The reason that is because we're working with triangles, and triangles have degrees. So trigonometry is only when you have right triangles. So we're still in right triangles. And what trigonometry does is it takes basically a ratio of an angle to a side relationship. So if you're just given one angle, let's say 30 degrees, and one side, then you, with trig, can solve for all the other missing sides of your right triangle. We know that if we have 2 sides of a right triangle, we can use Pythagorean theorem to solve for the opposite side. But if you just have one side and one angle, you want to use trig. And SOHCAHTOA is our memory tool for how we figure out trig. So stands for sine, S-I-N. Notice that button is right here. Opposite over hypotenuse. Remember, hypotenuse is the side always across from the right angle. Cosine, C-O-S, is adjacent over hypotenuse. And tangent, T-A-N, just down here, is opposite over adjacent. Okay, SOHCAHTOA. So we always want to keep that in mind when we're trying to set up our ratios. Sine is the opposite side over the hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Adjacent just means right next to you, right? So if we were looking at just our 45, 45, 90 triangles, just like we were earlier, and we wanted to use trig ratios, notice my x's have been turned into 1s, and my x radical 2 is just radical 2. But if you were just looking for sine of 45, then what you would do is start with the angle, and sine I know is opposite over hypotenuse. So the opposite of 45 is 1, over the hypotenuse, radical 2. So that's how you just get the ratio of sine 45. You put the opposite side over the hypotenuse side. Cosine of 45, cosine is the adjacent over hypotenuse. The adjacent side is the one right next to, so that's going to be your 1 over the hypotenuse, radical 2. Notice the radical 2 is next to the 45 as well, but he's not adjacent because he's always hypotenuse. Tangent of 45 is the opposite, which is 1, over the adjacent, which is 1. So that's why 1 over 1. So if I wanted to label my sides from this angle, this one is opposite, this one is adjacent, and this is hypotenuse. So that's how we get our ratios. 1 over radical 2 is sine, because it's s over h. Cosine is a over h. Tangent is over a. Let's look at another one. Trig functions of 30-degree angles. So this is our 30, 60, 90 again. From the 30 degrees, the 1 is opposite because he's directly across. The 2 is hypotenuse because he's across from the 90. And the radical 3, he's adjacent because he is right next to that 30-degree angle. So the sine of 30, I know it's so, ka, toa. So sine of 30 is going to be opposite over hypotenuse, 1 over 2. Cosine of 30 is adjacent over hypotenuse, radical 3 over 2. And tangent is opposite over adjacent, 1 over radical 3. And you'll see these exact same sets in your study section. And what I would do is just go ahead and copy those down as good notes. And then the same thing goes for the 60 degrees. Notice that it's the same ratios as what we just did, but now we're looking at the 60. So from the 60, the radical 3 is opposite. The 2 is still hypotenuse, and the 1 becomes adjacent because it is right next to the 60. So those are trig functions of your special rights, but you don't always need a special right triangle to use trig. Most of the times you use trig when you have just a crazy random angle, like 54. In order to solve for trig, the first thing you want to do is label your sides. So from this 54, the W is going to be opposite. The 10 is right next to, so he'll be adjacent. Remember your trig ratios, so, ka, toa. Notice my picture has an O and an A in it, so I'm going to use tangent of the angle equals opposite over adjacent. Okay, now this is where our calculators come in handy. Okay, because I need to get this W by himself, I'm going to multiply this side by 10, and it cancels. And I multiply this side by 10. So on your calculator, if you're using a TI-83 or TI-84, type in 10 tan 54 and hit enter. If you're using the calculator from Google, I would plug in tan 54, then times it by 10. Either way, you should get W equals 13.7. Okay. Let's try another one. So start with label, and then we will choose a trig function based on the letters that we see. And then the third part is we want to plug it in and solve for x. So label your sides from 28, opposite, adjacent, Notice I've got O and A again, so this is going to be tangent again. So tangent of our angle, 28, equals opposite 1.0 over adjacent y. Unfortunately, I can't just multiply by 1.0 on both sides like we could on this side because my letter's on bottom. If I wanted to get that letter by himself, I want to multiply by y, cancels on this side, and you multiply it on this side. He's still not by himself. He's stuck to that tangent, 28, by multiplication. So we have to cancel that out with division. Cancels. And then divide this side by tan 28. So you get y equals 1.0 over tan 28. Notice the y and the tangent actually just switched when the letter's on bottom. So I'm going to plug in 1.0 divided by tan 28. And I got 1.88. Go ahead and check your calculator. Make sure you get that same thing as I am. I heard somebody ding. Not sure who. Okay, Jillian, you got your hand raised. Did you get it? Can you use the chat feature to tell me whether or not you got that right? And that's why your hand raised, or if you're having a question. Okay. If you're not getting that answer, then what I'm going to do is I'm going to keep going, and then there's a spot here in a minute for questions. And if you're not getting these answers with me, then we can talk and try and get some answers to your questions here in a minute. The last type of problem I want to talk to you guys about is when you're looking for a missing angle. When you're looking for an angle, you have to use the inverse function. And if you looked at your calculator on if it's a TI-83 or TI-84, then that would mean you just hit the second button and then the trig function. And what that'll do is bring the sine inverse, or the cosine inverse, or the tangent inverse. If you're using the calculator from Google, then there's actually an INV button that you're going to press, inverse, and then the trig ratio that we decide. So notice here the problem is different because I'm looking for this angle. So we label our sides. The 12 is opposite. The 7 is adjacent. So again, we're using tangent. I'm sorry I didn't find some other trig problems besides tangent. But we're going to use tangent inverse. Whenever you're looking for an angle, you have to use the inverse trig function. So tan inverse of opposite over adjacent. So in my calculator, I'm going to hit inverse tan, 12 over 7. And just hit enter. It's super simple. You don't have to do any sort of multiplication or division. Just plug it into your calculator like this, and it'll spit out the degree of 59.7 degrees. Okay, we are almost done here, guys. I'm sorry, I know this has been a lot. Keep in mind, ratios just means your answer as a fraction. If you're looking for trig ratios, you want your answer as a fraction. So, for instance, what is the ratio of sine of A? Well, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So the ratio of sine of A is going to be opposite, which is the 3, over hypotenuse, which is the 5. And that would be my answer, because a ratio is a fraction. Just wants to leave it like that. Cosine of A, we know cosine is adjacent over hypotenuse, so that'll be the 4 over 5. And tangent of A is opposite over adjacent, which would just be 3 over 4. So trig ratios, you're just leaving your answer as a fraction, noticing those opposite, adjacent, hypotenuse, that sort of thing. All right, so this is the time for questions. So if you're not getting the trig answers right, please stay with me here for a second. And if you